Hey, welcome. My name is Chuck McCullough, and I will be hosting you during this live stream today. Today, we're going to get started with C++ programming. Today, our focus is going to be on getting set up, getting your tools ready to go so that you can start coding in C++ as soon as possible. All right, I'd like to welcome everyone that is with us live today, as well as all of you that are watching on the replay. Real quick, what we're going to be working with first is we're going to get our tools installed, as I mentioned. We're going to talk about data types. This is probably the most important thing that we're going to talk about today. We're going to understand how data is represented on the computer and how we are representing data in C++. We're going to write a quick program in C++. And we're going to talk about how we build executables in C++. User, if you're a Windows programmer, what do you need? So what I would recommend, there's a bunch of options, by the way, for no matter what your platform is, you have a lot of options. But what I'm going to recommend for you to get you started as quickly as possible in the Microsoft universe, Windows, what I'd like for you to use is Visual Studio. You can find that at visualstudio.com or visualstudio.com or visualstudio.microsoft.com. It is free if you download the community version. Now, your employer or your work may already have one of the licensed versions, professional or enterprise, and that's fine too. But you can download the community from that website for free. Now, there's a couple of different things on that same web page, so make sure you're looking at Visual Studio Community 2022. You're going to download that, run the installer. When the installer comes up, it's going to ask you what workloads you want. Now, if you're curious about C# and some of the other programming languages supported by .NET, feel free to install those workloads. But for C++, you're going to need the desktop development with C++ workload. That will get you a C++ compiler and all the tools you need in order to work in the C++ environment on a Windows desktop. Now, if you're on Linux, you have some other options. Now for the Mac, by the way, I don't want to leave the Mac out. Mac, you can use Visual Studio Community as well, or you can follow this Linux presentation. So for Linux, same website, visualstudio.com or visualstudio.microsoft.com. There's a different tool called Visual Studio Code. Visual Studio Code is an open source, multi-platform development tool for multiple languages even. It's not just for C++. And again, you don't have to use this. You can use any tool you wish. I'm just going to make this as a quick recommendation because it's a pretty good tool and it's easy to install and work with. So go there, install that Visual Studio Code on your system. Now, Visual Studio Code does not include a compiler, so you'll have to get that as well. From your Linux command shell, you just need to install, the best way to do it is just install Build Essential. Build Essential gives you everything you need for the GNU compiler and debugger and all of the tools involved with that. You'll need to be an administrator to do that, but you can do that with the sudo command and get that installed. All right, so I almost forgot, by the way, for you guys installing on the Linux platform, also after it is installed and you run Visual Studio Code, you're going to want to install some extensions. I think the minimum extension to install is the C or C++ extension from Microsoft. Just go to the Extensions tab and you can search for it. It will also recommend this extension as we start coding in C++ in a bit. So even if you don't find it and install it right now, it's going to come up later also. Let's talk about type. This is, I think, one of the most critical things in programming. And when I work with programmers that are having difficulty with their program, even if they have years of experience, one of the things that I run into all the time is that these programmers have difficulty because they don't have a real firm grasp of this thing called type. C++ is a statically and strongly typed language. So understanding type is going to be critical, essential to your understanding of how to make things work in your C++ world. Let me give you an example of what I mean. So what do you see here? You see the number 45. Well, or is it the number 45? Maybe it's something else. So how would you, if you just saw that, what would you say about it, right? Before you knew anything else. So if you have a little bit more of a mathematics proclivity, you might say, well, it's a whole number. It's a whole number. It doesn't have a fractional part, so we'll just say it's a whole number. But okay, it's a whole number. Somebody else might look at this and say, no, it's the letter 4 or the character 4 followed by the character 5. That it's not even a number at all. It could be the name of something. It could be a different meaning altogether. Who's to say? We don't know. But let's assume that it's a number, that it's a whole number. So what does it represent? Is this a person's age? Could be. That's in the right range for a person's age. Is it the temperature? It could be that too. It could be that as well. So we can say that it's a whole number, and we could say that it could be a temperature. It could be an age. It could be the distance between two towns in miles or kilometers, in centimeters. What does this mean? What's the meaning of this number? Regardless of what the meaning of the number is, its representation in the computer, inside the computer, is in binary. It's going to be 101101. That's that value on the computer. Because the computer doesn't even really represent numbers in base 10 like 45. It only has ones and zeros. Computers only know binary. All information that we present on the computer has to be presented in ones and zeros, represented as ones and zeros. So what about that 45? How did we get the number 45 represented on the computer? Well, so that was 101101. So just like you count in tens, so the first digit is the ones, the second digit is how many tens do you have, the third place over is how many 100s do you have, the fourth place how many thousands. So powers of 10. When I count in binary, I'm counting in powers of 2. So the first digit, how many ones do I have, followed by how many 2s do I have, how many 4s do I have, how many 8s do I have, and so forth. So for representing the number 45 on the computer, I need to light up the ones where the 32 plus an 8 plus a 4 plus a 1. Add all those together, there's your 45. So that's how we represent that in binary. If I turn on all the ones, I have a 28, a 64, a 32, etc., I can represent values, integer values, between 0 and 255. Adding all those up together is 255. So that's the range, that's the limit of range if I use these 8 bits. So we're looking at each of those ones and zeros is called a bit. It's a switch. The computer's memory has millions of these switches, trillions of these switches, and the CPU has banks of switches as well, and the CPU knows how to do certain operations, certain math operations, adding, subtraction, and things like that on these binary numbers. So as a human, I think about 45. The computer sees 0010, 1101, and it knows what that means. And by the way, that's it. That's all the computer really knows how to store is ones and zeros. And we can read those ones and zeros, here a group of 8 of them together, and say that that's the number 45. What if I looked at more bits and looked at 16? Then I could represent a larger range of numbers. I could even give different bits different meanings. For instance, what about floating point numbers? Computers know about floating point math, right? No, not really. Not really. Sort of. They emulate it because the computer still just has ones and zeros. And when it comes to floating point numbers, it's almost like we need fractions of a one or fractions of a zero, but we just have one and zero. It's on or it's off. So what we do with floating point numbers, or what the computer does, is some of those bits represent the integer, the whole number, and others tell where the decimal place goes. So how far to the left or right within the number are we going to place the decimal place? Now, the computer doesn't do irrational numbers very well, so at some point we have to cut it off. On the computer, there is a number of decimal places, a number of digits that it's able to represent, because it ultimately is just a whole number that is representing. And we're going to put that decimal place somewhere within that number. So we're approximating floating point numbers. If you're talking about irrational number like pi here, which never ends, the digits keep going forever, then we can't represent that completely, but we can approximate it. We can get close. All right. What about text? What if I wanted to store or manipulate or display the text "Hello World"? What about characters? Well, they're still just numbers. The computer doesn't really know about characters per se. It only knows about numbers. And so what the computer industry has done, they've defined a couple of lookup tables. These tables, called Unicode for internationalized symbols, or ASCII for the Western alphabet, these characters map to numbers. So for instance, the H in the Hello World is represented as the number 48. 1001000, 48. And the next letter E, the little e, is a different value. It's off the top of my head, I don't remember, but it's out there. It's like I don't know. It's about 27 or 28 plus that, so 70 something, I would guess. So the lowercase and the uppercase letters are mapped, as well as punctuation characters, semicolons and dots and tabs and all kinds of things like that. They're represented, they're assigned a numeric value. And things like our video cards, they know how to draw those characters graphically based on that lookup table that we're using. The Unicode table takes up 16 bits worth of information, so it can represent a larger range of characters so that it can include characters from other character sets, Chinese and Kanji and Hebrew and Arabic, etc. So the computer CPU is hardwired to understand certain data types, certain fundamental data types. So what does the CPU's circuitry, its electrical engineering, what does it know how to do? It knows how to represent and manipulate, perform math on integers, whole numbers. It knows how to work with floating point numbers, numbers with a decimal place. And again, it's an approximation because it's really internally just an integer with information about where the decimal place goes. It understands Boolean, true or false. Is something true or false? 0 for false, 1 for true. It also does understand characters, so mapping integers to human readable symbols in our natural language, A through Z, or other symbols and other character sets, including the punctuation characters and smiley faces and copyright symbols and everything else that we visually see as humans. Those are assigned a number so that we can interact, so that the computer can interact with humans. All right, that's all the computer understands. We are going to be designing and implementing in C++ very sophisticated applications that work with data that is far more complex than any of these. However, no matter how complicated your data is, we can always break it down to these things. You can think of this as the atoms of the computer. And everything else that we talk about will be some type of more complex molecule that's made up of these fundamental atoms, the integers, the approximation of floating point numbers, Booleans and characters. From there, we can build any complex data type. We can represent cars and humans and circles and rectangles, all kinds of different things. Before we do anything else, and the reason I wanted to talk about fundamental data types today as you're getting set up for C++ programming is ask yourself, what is your program going to be doing? Let's think about that. What are we going to do with our program? That needs to be planned first. Okay, so if you're going to bake a cake, you need to know what ingredients you need for making the cake. You're going to need some flour, you're going to need some butter, you're going to need some eggs, etc. So where are you going to get those? Do you have them already? Do we need to go buy some? What kind of flour, etc. So before you would start baking the cake, you're not going to just get the pans out and start throwing stuff in there and hope it turns out. You're going to look at the recipe, should read the recipe first in case there's a surprise at the end, because some recipes you get down to the last step and it says, oh yeah, I forgot, before you put your stuff in the pan, make sure you butter it. So read through the recipe first, see if there's any surprises at the end. That's your plan. You're understanding the plan. Next, see if you've got all the ingredients. And if you need to go to the store, go to the store and get some ingredients. Now that you have your ingredients and you have previewed the recipe, you know how to go through those steps. Writing a program is no different. The first thing I want to ask, what is this program supposed to do? Who's going to use it? What are we trying to accomplish? What are the inputs and what are the outputs? So your recipe, the inputs are the eggs and the flour and the milk, etc., and the outputs are the cake. What are our inputs and outputs? What information is your program using? And how are you going to describe and represent that information? Because I've given you the four basics that everything has to boil down to: whole number, integer, floating point numbers, Booleans, and characters. So we can build up any complex information from that, but we need to understand what information your application requires first. So let's say that I ask you to do something simple. Write a program that converts Fahrenheit temperatures into Celsius. So what information is involved? What kind of data do we have? Well, if we're converting from Fahrenheit to Celsius, then I'm assuming you have temperatures in Fahrenheit. So like earlier, 45, maybe that was a temperature. 40 degrees Fahrenheit. So if that's what the data looks like, then that looks like a whole number to me. That looks like we could represent that as an integer. Or what if some of the data has a decimal place? Well, if that's the case, then we'll call it floating point data. Now, there is a trade-off, by the way. It does take more CPU time and more memory to represent floating point information than it does integer information. So we ask the question, do you need the fractional part? Do you need that? Is that accuracy necessary? Or would it be okay if we just work with whole numbers? So the customer or whoever's using your program would say, no, we need to have this to be accurate within 2 or 3 or 4 decimal places. We better use floats then. No, whole numbers are fine. I don't care about the fractional part. Then we can use integer. So we have to make that analysis. We have to make that decision. Same thing making your cake. The cake recipe calls for unsalted butter. I don't have unsalted butter. I have salted butter. Is that okay? Can I use that? I don't know. If you're happy with the cake being a little more salty, it has some other effects on the recipe as well. So what range of values are going to be used? So we're going to convert Fahrenheit to Celsius. Is that any any arbitrary number like -4 billion degrees Fahrenheit, or is there some range? Well, there's absolute zero. Absolute zero is as cold as it gets. And then there's got to be some maximum temperature that we would care about. If you're building a thermostat, if you're writing software for a thermostat, then you really don't even care about absolute zero. Pretty cold is cold enough. What's the normal human range of temperatures? So something within a reasonable range, 100 degrees maybe, from 0 to 120 degrees or something like that. Again, let's talk about that. What's the range? Because I need to know that so I know how many of those bits I need, and so that I can make sure that we're not working with invalid information. Do I need the decimal place or not? So those are the questions to ask. Those are the questions to ask. Now, C++ supports primitive data types that pretty much align with the data types that the computer understands. So C++ has representation for those very basic data types. So what C++ calls int, I-N-T, is an integer. And there are several different varieties of integer. We'll get into all of that a little bit later, of signed numbers that can have a negative value, as well as unsigned, positive only, with different size ranges. So we can talk about integers that range from 0 to a few thousand. We can talk about integers that range from negative billion or so to positive billion or so, or even larger ranges of signed, unsigned. The question is, how many bits does it need, and what range, and is there a sign or not a sign? So that making that decision, so that's why we spend time analyzing what kind of data are we going to have. With the Fahrenheit temperatures, if we're going to need negative numbers from maybe -100 to say +300. So we need that range of value. So I need to look at the variety of int types within C++. I know it's going to have to be signed, and I know that I don't need a huge range, but a few hundred degrees would be fine. So we'll pick an appropriate int, and we'll go over those in a future session. Or is this going to be floating point? Do we wish to have more precision than the integer? So if that's the case, then I have to ask the question, how much precision do I need? C++ has two varieties. It really has more than that, but we'll talk about them. Two basic varieties of floating point numbers, float and double. Float has about 7 digits worth of precision, and double has about 15. Now there's also a long double that has even more. It has close to 30 digits of precision. We'll talk about that one a little bit later. C++ has a Boolean data type that represents true or false. It also has a data type called char, or some people say char, that represents a single ASCII character. A single ASCII character. So it has a number range of 0 to 255, and the ASCII table, the ASCII lookup table, tells us what character is represented by each different value. It also has a type called wchar that represents a single Unicode character. So that's about 65,000 different possibilities there, representing all of the different character sets in the human experience. Those are our C++ types, and we can use those, like I said, to build up and create more complex types. But these are the atoms. These are the atoms that make up the basic. We'll build the molecules from there. All right. Let those sink in. Think about type. Think about how you want to represent information. And if it's more complex information, like someone's salary, how do we represent that, right? Maybe float or double would be appropriate. So type is important. We have to think about type. Now, once you have your C++ compiler, What do I mean by compiler? What do we do with that? What's the purpose? Well, as a programmer, if I'm going to write a program in C++, I'm going to work with the source code. That's the human-friendly part of C++, of programming. The C++ programming language has words and phrases and a grammar and a syntax just like English or French does. I'm going to tell the computer what I want it to do using the C++ language and its syntax, its grammar, and I'm going to write that in a plain text file. By tradition, that plain text file will have an extension of .cpp. It could have other extensions. Other groups may use something different. That does not mean anything to the computer. The computer has its own instructions that are ones and zeros. So we can tell the computer's brain, its CPU, what we want it to do, but we have to set the ones and zeros in the right places, and then we can tell it to add and subtract and multiply and branch and make decisions and things like that based on those values. So that has to be created as a binary, ones and zeros, not very human friendly, but the computer knows what to do with it. The compiler is itself a program that someone wrote that translates our C++ human-friendly source code into something that's readable and usable and meaningful to the CPU, to the computer. So the compiler does that translation. C++ is a programming language that does that statically. In other words, we only do that once. So we'll take our source code, we'll convert it into the binary, and then we copy that binary file to the target computer, and that's where we run it. And we can run it anytime we want, run it over and over and over again from that binary image. If I make a change, if I alter the program, I'll have to run it through the compiler again. But then I can run that program over and over and over again. We never need the compiler again after that to just run the application. Now, there are other programming languages that don't quite work that way. There are even programming languages that don't even have a compiler. They just translate the source code. When you run it, it gets translated to the binary on the fly. So you never have a binary, you just run it. Our batch programming languages, Perl and Python, those are programming languages. We call those interpretive languages. So they run within a program. You run the program first. That program was probably written in C++. You run that program first, and then you type in your instructions, and it translates them in real time. That takes a lot longer. It doesn't run as fast, of course. Run the Visual Studio Code from the command shell just by typing code and then the directory that I want it to open. Now, ignore this stuff. We'll talk about all of these things a bit later. I'm going to type in a simple C++ program, and we'll go over in future streams what all of this stuff means. So I'll specify what text I want to output, followed by a new line character. You know, they call this code for a reason, because sometimes it looks a little cryptic to normal mortal humans, but for us superhuman programmers, this has meaning. We understand what this means. Now, from my command shell, there's that file. The compiler, in my case, is called G++. I'm going to tell it to compile hello.cpp, and I want it to produce for the output something called hello.exe. So, oops. Sometimes I have an error. I forgot. I put void and I meant to put int. That's what happens when you're talking and typing at the same time. Not a problem. Let's do that again. So it ran successfully this time. So you'll notice it produced this binary. Now, you can try to open that file, hello.exe, in a editor or something, but you'll just see that it has a bunch of characters that don't make any sense. When I run the application, it outputs the text that I told it to output. So it produced the output that I expected, and I can run it over and over and over again. I don't have to compile it again. So what we mean by a static compiler, you only have to do it one time. It's not dynamic. It doesn't require that you run it every time the way that interpretive languages do. All right. All right, well, that brings us to the end of our live stream. I'd like to thank everybody that's watching this now and in the future. We will continue with this series of live stream with starting next week, same time, same channel, and we will start into the C++ syntax and how to write programs in C++. Between now and then, you have a chance to get those tools installed, verify, write the little program that I did, the Hello World, and make sure that you can produce the output. If you're using Visual Studio Community, you simply have to create a C++ console application, type in the code. You don't even have to open a command shell. It will take care of all of that for you. All right, thank you for attending, and we'll see you next week.